So in this video we want to explore the sine function and understand why it looks the way that it does. So just like we did with the cosine function, what we want to remember is that we have already demonstrated that for an ordered pair xy on the unit circle, that ordered pair can be described in terms of the cosine of theta as the x-coordinate and the sine of theta as the y-coordinate, where theta, that's a horrible line right there. I have to erase it. I have to redraw it. So what we've identified is that theta is the angle that is in standard form. So it starts at the positive x-axis and rotates around to the terminal side as delineated by the point xy. So xy, that point, gives us a terminal side for our angle theta. And from this we know that y is equal to the sine of theta. So just like we did with the cosine, we want to recognize that the implication is that on the sine function we have ordered pairs, and the ordered pairs are input theta. You input the angle that you've swept out as you rotate around the origin on the unit circle, and the outputs are the y coordinates on the unit circle. So if we have a function f of theta equals sine theta, the outputs to that function sine theta are just going to be the y coordinates on the unit circle. And so once we understand that the outputs to the sine function are just the y coordinates on the unit circle, we can begin to understand what the graph of the sine function looks like. So here's the sine function right here, and what we want to notice is that it starts out at the origin. The eraser tool is not coming up very easily. So it starts at the origin, so at that point 0, 0. And the input is the angle in standard form, and the output is the y coordinate on the unit circle. So on the unit circle we see that when we start out at 0 degrees or 0 radians, we are at the coordinate 1, 0, so the y coordinate is 0, and therefore it's the output to the sine function. So the sine function has the point 0 degrees 0 or 0 radians comma y coordinate of 0. And then as we sweep around the unit circle counterclockwise, so here I've swept, I'm at an angle of 61 degrees, so I have a 61 degree angle sitting here. So on the unit circle the y coordinate is 0.87, so on the sine function the output is also 0.87, and the input is either the degree or radian measure that you swept through. So this ordered pair right here in degrees would be, hey, we've swept through an angle of 61 degrees, and right now the y coordinate is 0.87. And that angle can be measured in either degrees or in radians. And as we continue to sweep, we reach 90 degrees, and when we're at 90 degrees, what we want to notice is that the ordered pair is x0, y is 1 on the unit circle, so the output to the sine function should be a 1. The output on the sine function should be a 1. So right here we have the ordered pair, the eraser tools being so the ordered pair here should be, hey, I'm at the 90 degree mark on the unit circle, and the y coordinate is a 1. So this number needs to match the y coordinate on the unit circle. And as we continue to sweep along the unit circle, we're going to wind up at the 180 degree or pi over 2 mark. So at 180 degrees, we have the ordered pair on the unit circle, x is -1, y is 0. So at the 180 degree mark right here, input 180 degrees or pi radians, the output should be 0 because the y coordinate is 0. So again, we're really graphing the y coordinate on the vertical axis as a function of theta on the horizontal axis. As we sweep back around to the 270 degree mark, here we're at a 270 degree rotation, or 3 pi over 2 radians. We see that the y-coordinate at this point is going to be a -1. So the output on the sine function at 3 pi over 2 radians, or 270 degrees, should be a -1. And when we sweep the rest of the way around at 360 degrees, which is coterminal with 0 degrees, we're back where we started. So just off the screen here, there's going to be an input of 360 degrees and an output of 0. We're back where we began. And then as we continue to move around the unit circle, or rotate around the unit circle over and over again, this picture is going to repeat itself infinitely many times. If I rotate either clockwise or negative angles are going to be clockwise rotations, because negative angles depict clockwise rotations on the unit circle. So if we zip back to PowerPoint, we can summarize the discussion that we just had very quickly. So exit, yes, exit that, and bring PowerPoint up and start it. So we can summarize what we just did. What we want to recognize is that the sine function maps y-coordinates as a function of theta. And so it would be probably more appropriate right here to say, for the sine function, the input's theta and the outputs are the y-coordinates. So the y-coordinates are the functions of theta. And because on the unit circle, when we start in the 0 degree position, we're at the point 1, 0. The y-coordinate is 0, so at the 0 degree mark, we should have the ordered pair input an angle of 0. The y-coordinate is 0 because the inputs are the thetas and the outputs are the y-coordinates on the unit circle. We're going to sweep through 90 degrees and wind up at a high point of 1. We sweep through 90 degrees, we wind up at, hey, when I've swept through 90 degrees, the output is 1 because the y-coordinate is 1. When we're up here, then we're going to rotate through another 90 degrees to the 180 degree mark. And when we get to that point on the unit circle, the y-coordinate is 0. So we're at -1, 0. The y-coordinate is 0. We're back at 0 at that 180 degree mark. And then we're going to sweep around to the 270 degree mark, and the y-coordinate there is going to be, where x is 0, y is -1, so we should be down at a -1. So 270 degrees corresponds to -1. And then we rotate back to 360 degrees, which is coterminal with 0 degrees, which means we're back where we started at 360 degrees. We're back where we started at a y-coordinate on the unit circle of 0. When we think about the domain, we're really asking the question, what are the possible angle values? Because the inputs are angles, theta. So where can theta go from? And we want to recognize, just like we did with the cosine function, that I can rotate infinitely many times counterclockwise. So I can go to infinity in terms of my angular rotation counterclockwise, and I can start in standard position and rotate infinitely many times counterclockwise or clockwise. So theta isn't restricted. How we rotate around the unit circle isn't restricted. We can rotate infinitely many times clockwise or counterclockwise. But in terms of the y-coordinates, we can get as high as 1 and as low as -1. So we can get as high as y equals 1, and we can get as low as y equals -1 on the unit circle. So those are the only possible values for y that we can get. They have to range from -1 to 1. And the period is 360 degrees, or 2 pi radians, because everything that happens to the y-coordinate on the unit circle happens as you rotate one time around the unit circle. When you rotate again, everything will just repeat itself all over again. So the period is 360 degrees. So just like with the sine function, my tip for graphing, or sorry, just like with the cosine function, my tip for graphing the sine function is going to be exactly the same. We want to recognize that the sine function, sine of theta, is the toolbox function for all possible sine functions. This is our toolbox. And it always has the same shape. It always starts at the origin, sweeps through to some high point, sweeps back down to 0, an output of 0, sweeps down to an output of -1, and then sweeps back to an output of 0. And so what you want to do is draw the shape that the sine function has to be, and don't put tick marks in first. Once you've drawn what it needs to look like, then put in your tick marks. You know the high point is 1, you know the low point occurs at -1, and you know that everything that happens on the unit circle happens in 360 degrees or pi radians. And then you look at the special points on the graph. The quadrantal angles correspond to the high points, or the zeros. These are your quadrantal angles. So this is 90 degrees, 180 degrees, 270 degrees, 360 degrees, all multiples of 90 degrees, 90 times 1, 90 times 2, 90 times 3, 90 times 4, or break pi up into, sorry, this is 2 pi here, one full rotation, one full revolution around the unit circles, 2 pi radians or 360 degrees. And then we break 2 pi radians up into 4 pieces. 2 pi divided into 4 pieces is pi over 2. So 90 degrees corresponds to pi over 2 radians. 1 pi over 2, 2 pi over 2, 3 pi over 2, and right here is 4 pi over 2, which reduces to 2 pi, and 2 pi over 2 reduces to pi radians, which is equivalent to 180 degrees. So again, graph first, then put the tick marks in, instead of putting tick marks first and trying to fit the graph to the tick marks.